In this video, we want to talk about discrete random variables. So we're changing things up a little bit and moving forward into a new topic, discrete random variables. We're going to start with a claim. Read an article several years ago that said 30% of all college students have a tattoo. 30%. And at the time, I looked at that number and I thought, that number seems kind of high to me, but I was sort of out of touch with the tattoo world at the time. I was a little older than the standard college student age, and I thought, who knows, maybe that's right. So what I decided to do is randomly sample 5 college students to find out how many of the 5 have a tattoo. And the idea that we're building towards, we've worked with some descriptive work where we describe both numerically and graphically the information in a sample. Where we're moving to is, can we take the information in the sample and make some kind of statement about the population? In this particular example, 30% is a number that describes all college students, the population. And so what can a sample tell us about that value? For instance, if we took a sample of 5 college students and found that none had a tattoo, would that surprise us? How about if all 5 had a tattoo? Would that surprise us? And that's what we're building towards. How do we do the inferential statistics that we've talked about so far? And so here's what I want us to think about. Possible outcomes. And sometimes we take a look at this type of work in a probability setting. Sometimes we don't, and I generally wait till I talk about discrete random variables. But here's an idea. Think of these outcomes. Now, what is this? T's and N. What the heck is going on here? These letters represent individual students. You'll notice that they're in groups of 5. So this first outcome here, where I have 5 T's across the board, let's say I randomly sampled 5 students and they all said they had a tattoo. The first one said they had a tattoo. That's what this first T represents. And the second, and the third, and the fourth, and the fifth. They all said they had a tattoo. Look at this one over here. None of the 5 students said they had a tattoo. And you can see, or you can imagine at least, that there are a lot of combinations of N's and T's. Think of all the different combinations. In fact, there are 2 to the 5th, or 32 possible outcomes. Where does that come from? Well, this first student here, how many different outcomes can they give me? If I ask you, do you have a tattoo or not? If I asked you, do you have a tattoo? You're either going to say, yes, I do, or no, I don't. You're either going to give me an N, no, or a T for tattoo. And so there's 2 outcomes possible in this first student. There's 2 on the second. There's 2 on the third, 2 on the fourth, 2 on the fifth. And you end up multiplying those outcomes together for 32 possible outcomes. And actually, in my office, I have a stack of index cards where I have each of those 32 outcomes on them. I have 32 different outcomes on 32 different index cards. And there's just a small stack. And it's a nice way of thinking about the things that can happen. Because here's where we're going. If there were 50 students, there are going to be 2, not to the 5th power like we saw here, but there'd be 2 to the 50th power outcomes. And when you put 2 to the 50th in your calculator, my calculator took a little bit of time, but it's 1.126 times 10 to the 15th. When you start multiplying by 10 to the 6th, I think you're in millions. 10 to the 9th is billions. 10 to the 12th is trillions. What's 10 to the 15th? It's some kind of illions, and it's a big number. That's the point. And what I like to tell students, if I took a standard index card like I did up here, I have 32 index cards with these outcomes. If I took the standard index card and tried to write out all these outcomes, first I'd never be able to do it. But if I did and I stacked them up, what I'd like to tell students is that stack of index cards would go 2.3 miles into the air. Think about that. 2.3 miles of outcomes. Then I like to tell students that I'm absolutely lying. I have no idea. But the point is, and I think you understand, my point is there's a lot of outcomes. When we went from 5 students to 50 students, look what happened. It exploded, the number of outcomes. I can keep track of these guys. That's not too bad. 32, I can do that. 1.126 times 10 to the 15th, I have no chance. And so this outcome idea, which is a very probabilistic, like a probability chapter type of idea, we move beyond very quickly. After you talk about 6, 7, 8, 9, 10 outcomes, 2 to the 10th, or what would that be? Let's see, 32, 64, 128, 256, 5, 12, 1,000 outcomes. 2 to the 10th is 1,024 outcomes. The number of outcomes just skyrockets, and it's impossible to think about this. So we need a different way. That's the point. The point of this discussion is that our probability techniques are thinking of outcomes in terms of letters, and it doesn't work. It doesn't work. So we need a new way, and that's where the definition of a random variable comes into play. A random variable is a variable that assigns a number to every outcome of an experiment. So we can think in terms of the letters. We can think in terms of the T's and N's, whether we're dealing with 5 students or 50 students. But we say, you know what? Rather than think in terms of T's and N's, let's think in terms of X. And we typically use letters like X, Y, and Z, although we'll see later Z is kind of reserved. But X is, in this case, the number of the students with a tattoo. And so when you look at your 5 students, X is going to be the number of students with a tattoo. Y is going to be the number of students with a tattoo that says, I love statistics. Now, typically when I teach a live class, typically I teach large sections. And so I'll randomly sample 5 students. And I use the word random loosely because typically I choose 5 students that sit near the front. And I ask them, do you have a tattoo or not? And from one semester to the next, from one class to the next, the answers vary. But typically in a sample of 5 students, I'll either have 0 or 1 or 2. I think one semester I had 3 students with a tattoo. I don't know if I've ever seen 4 or all 5 with a tattoo. But then typically at the end, after I take my sample, I'll just kind of casually look over to the students and ask them, do any of you have a tattoo that says I love statistics? And I haven't found that student yet. I'm surprised. I thought it would be a more popular tattoo, but apparently it's not. So why is the number of students with a tattoo that says I love statistics? I think I'm going to get a lot of no's, like N, no matter how many students I sample. Now, statistics teachers, that's another story, but we're not going to go there. So X and Y are just going to be some definition that assigns a number to the outcomes of an experiment. So when N is 5, if you think about the values of X, if you look at a sample of 5 students, we saw the outcome where we had 5 N's going across the board. The value of X would be 0. None of those 5 students. Let's say I look at a sample of 5 and the first student says no, the second says yes, and then the rest say no. Well, one of those 5 students. And you can think of those 32 outcomes, and this is how I like to think about it. We can think of those 32 outcomes as falling into one of these values of X. Any combination of N and T you think of when you're working with 5 students is either going to have 0 or 1 or 2 or 3 or 4 or 5 of the students that have a tattoo. And so I like to think about it, and when I'm in class and I actually have the index cards, it's easy to see this. But think about having a deck of index cards. Think about having 32 index cards where I have those 32 different outcomes. And I'm really sorting those cards based on their value of X. So where I see all N's going across the board, well, that's the 0. That's the outcome where X is 0. If I have the one that have T's going across the board, well, that's the one where X is 5. And what you start to realize is there's several cards that have 4 students with a tattoo. Think about how many different ways you can write the T's and the N's where you have 4 T's. Well, if you have 4 T's and there's 5 letters on the card, isn't there one N? I can move that in. Maybe it's the first student who doesn't have the tattoo. Maybe it's the 5th. Maybe it's the 3rd, the 2nd, the 4th. And so that's the way I like to think about these random variables. And a lot of times students say, well, you're taking those 32 outcomes that we talked about, and you're putting them into, and a lot of times students say 5 different values of X, and really it's 6 values of X because of the 0, 1, 2, 3, 4, 5. There's 6 different values of X. But really what I'm doing is I'm sorting those 32 into their 6 different values of X. And a lot of times students say, well, what's the big deal? You had 32, now you have 6. It's not that big a deal. Now it's a big deal. When N is 50, I have that, what was that number? 1.126 times 10 to the 15th. Look back on the previous slide. That's a lot of different values. It's really difficult to keep track of all those different outcomes. Well, I don't have to keep track of all those different outcomes because I can slide all those outcomes into 51 piles, into 51 different values of X. And so the point is we want to move away from the outcomes. And again, I typically don't look at outcomes all that much. I just kind of introduce the idea here and then quickly show you that it's not a real efficient way of working with experiments and outcomes, and it doesn't work real well. And so we want to move away from those outcomes and more towards the values of X. Okay, so when N is 50, if I took 100 students, the value of X would be 0, 1, 2, 3. It wouldn't stop at 50, it'd stop at 100. If you try putting in 2, and I have a little calculator here, let's see what happens. When I put in 2 to the 100th power, I get, let's see, 2 to the 100th power is 1.267 times 10 to the 30th power. These numbers are exponentially big. It's huge. And so that's not the way we're going to approach it. We're going to approach it from a random variable way. Assign a number to every outcome of the experiment, and we're going to try to look at things that way. All right. So that's what a random variable does. Let's talk for a second about the different types of random variables, because there's two types. And the type of random variable is going to be dictated by the values that get assigned. The first type are called discrete. And the variable assigns a countable number of values to the outcome of an experiment. Now this phrase countable number here, this thing right here, it's a math type of word. You guys typically, most times when students hear the word, they don't have any problem with it. Oh, countable, yeah, I can keep track, I can count. Unfortunately, a lot of times students think finite, which isn't really right. I'll try to explain it in a second. Let me give you some examples. The number of students with a tattoo, the example that I've been talking about. If you take a sample of 5 students, the number of students with a tattoo would represent discrete. It's either 0 or 1 or 2 or 3 or 4 or 5 or up through n. And a lot of times students are like, yeah, I can count that. 0, 1, 2, 3, 4. Got it. The number of cell phones that ring during a class. Now this is the one I want to try to expand your thinking about it. Think about a traditional class. You're sitting in class. Maybe it's a big lecture auditorium. And again, that's typically what I teach. A lot of times during class, something will go off, whether it's a vibration or a ringtone, and a lot of times students are real quick to catch it. But what's the fewest number of cell phones that can ring during class? Well, everyone says 0. And you get those classes when none go off. Students are pretty mindful of it. Could 1 cell phone go off? Sure. How about 2? How about 3? Here's a question. Could 3.5 cell phones go off? No, right? It's either 0 or 1 or 2 or 3 or 4. Now, it's funny because when I teach this class in a live setting, I do something with my hand to kind of indicate what's going on, and I'm finding myself sitting here videoing this, and I don't, of course, have a webcam on, but I'm sitting there and taking my hand, and I'm making like a chopping motion. And when I say it's 0, my hand goes down, and then when I say or 1, as I say or, it kind of goes up and then goes down when I say 1, or 2, or 3. Or 4, and my hand's kind of chopping up and down. And that's what I want you to think about with discrete. The word I want you to think about is jumps. So what the heck does that mean? The values of the random variable jump from one value to the next. It's either 0 or 1 or 2 or 3 or 4 or 5. Now, the number of cell phones that ring during a class. Let's kind of stretch this out and go with me here. What's the biggest number? And someone usually in the class will say, well, it's the number of students in the class. I say, is it though? Let's say I'm teaching a big lecture room where there's 100 people in the auditorium, and we talk about the number of cell phones that go off during class. Is it limited to 100? Couldn't your cell phone go off more than once? And so students say, yeah, it could, yeah. So what's the upper bound? Well, there's a type of random variable. It's called the Poisson distribution. It looks like poison, but it's got a second S in there. Poisson is generally how I say it. It's French. The values of x are 0 or 1 or 2 or 3 or 4 or 5 or 6. And again, I'm doing a jumping, or 7 or 8 or 9 or 10. It goes on forever. It goes to an infinite number of possibilities. And that's where this word countable screws students up. They're like, wait a second. Infinite's not countable. Yeah, it is. Mathematically speaking, it can be. Doesn't have to be. It can be, though. And so I don't really want to get caught up too much in this word countable. What I really want you to think about is the fact that it jumps from one value to the next. The number of cell phones that ring, it's either 0 or 1. You can't have half. You can't have a third of a cell phone ring. I don't care if it's just the first note of your ringtone. Once it goes, that counts. And so it jumps from one value to the next. It doesn't always have to jump on whole numbers. A lot of times it does. The number of questions you get wrong on an exam, it's either 0 or 1 or 2 or 3 or 4, up to the number of questions that are on that exam. A lot of times you see whole numbers or integers. It doesn't have to be that way. It could be fractional. I remember once I had a scale that gave me my weight. It was a digital scale. It gave me my weight to the nearest half pound. So when I got on a scale, it either said 170 pounds or 170 and a half or 171 or 171, and it jumped it by every half pound. But the fact is, it jumped, and that's the point. It jumps from one value to the next, and that's what makes it a discrete random variable. Now, the reason that I'm talking about these two different types, discrete and continuous, the type of random variable that we're working with helps us try to figure out how we're going to work with it. There are different, what I like to call tools. There are different tools that we use for discrete random variables than for the second type, which are going to be called continuous random variables. And once we identify that there's a discrete random variable that we're working with, we open up our discrete toolbox and say, all right, what's going to work? Which of our techniques in here is appropriate for this discrete random variable? And if we have a continuous random variable, we go to the other toolbox. And we say, all right, what's available over here? And we're going to look at a tool for each of the two different types. So that's the discrete. It jumps from one value to the next. Okay, so that's jumping motion. And again, I'm sitting here as I'm filming this, my hands going up and down as I'm talking about these different things, and you're not getting really a benefit of seeing it. Hopefully I'll be able to explain it in a little picture you're going to see on the next slide. All right, so let's talk about the second type, continuous. It's the non-jumping type. The variable can assign any value in an interval of values. And to give you some examples, and again, the examples here kind of help. The length of time it takes a person to drive to work. I live in just north of Tampa. Typically when I teach at the Tampa campus of the University of South Florida. And I live in a small town called Lutz, just a little north of campus. And it takes me somewhere, I like to tell the students, my perfect drive takes me 12 minutes. It's when the lights are perfect and there's no school buses and there's no traffic, and my perfect drive is a 12-minute drive to work from door to door, out my driveway into my parking spot at the campus, 12 minutes. It takes me longer than that sometimes, though. In fact, it usually takes me longer than that because stuff happens. Red lights happen. Traffic happens. School buses happen. One of the roads I drive on is notorious for school buses in the morning. So if I have an early class, I got to plan for a little bit longer time because it can take me 15, 20, 25, 30. In fact, it's taken me as long as 45 minutes to drive to work. But when I think about the different times it takes me, so pretty much my extremes are from 12, that's my shortest time that I've ever been able to drive, the perfect drive, to 45 minutes. Really anywhere in between there's possibility. And I'm sitting here and I got, when I say 12 and 45, I got my hands kind of in the air looking at those endpoints, and then rather than jumping from one value to the next, rather than saying, well, it's either 12 or 13 or 14, my hands just kind of swishing back and forth between the endpoints, because it could take me 12 and a half minutes. It could take me 15.74 minutes. Any value in there is possible. It's not jumpy. The height of a student. If you get a whole bunch of students together and you ask how many of you guys are 6 foot tall, a bunch of guys will raise their hand. Are they all exactly the same height? No, we all kind of round, right? We all, like my scale rounded to the nearest half pound. My weight really wasn't a discrete variable. It was more of what we're going to call continuous, but my scale rounded to a discrete measure. And so when I looked at the scale, it jumped from one value to the next. But the height of a student or the weight of a student is a continuous measure. Someone could be 6 foot half an inch, 6 foot a third of an inch, 6 foot and 7/10 of an inch. And so it's a continuous measure. I'll give you another one. The amount of soda poured into a 12-ounce can. Think about a soda can, and we'll probably talk about this later when we talk about one of our tools for working with continuous random variables. But when you get your 12-ounce soda, it may not have 12 ounces. It might have 11.8882 ounces, or it might have 12.01117 ounces. There's a continuous measure. It doesn't jump. The nature of the variable you're collecting is what I'll say smooth. The continuous random variable has no jumps. It's smooth. Anywhere in between is fine. Now, this little picture, you're probably thinking, what the heck does this have to do with these random variables? I was looking for some clip art where I had a nice stream and I could draw some pictures, and I really didn't find anything I liked, so I got this picture from somewhere. And the reason I chose it is because there's a bridge. And I want you to think about water, and I was looking for like a stream or a creek, and I got a little bit of a more rushing water than I wanted. But let's say you're standing, and this is going to be my beautiful artwork here. This is you. This is stick figure you, and you want to get onto the other side over here. Well, if you're going to take a discrete path, if you want to try to get from one side to the next, what you're going to try to do, and I always like doing this, maybe not with this kind of rushing water, but I like doing this with streams. If I go hiking or something, I'll try to find a stream or a creek, and I like playing around in the water and jumping from one rock, one landing point. So here's a rock here, and it looks like maybe there's a rock maybe here, And then there's this a bit looks like a rock, and then I got this big rock here. That's a nice landing spot for me. And then if I'm looking beyond that rock, I think I see one here, and I see one here, and I see one here, and then eventually I'm going to get somewhere over here, jumping from rock to rock. I'm going to get to the other side, and I'm going to end up over here, taking my jumps from one value to the next. And that's kind of jump from one value to the next. I'm going to make a big jump here and then come back and then go here. That's kind of the discrete path across this water. And that's what I want you to think about with a discrete random variable. You jump from one value to the next. Now, if you say, well, the heck with that, I don't want to take the discrete path. I'm going to take this bridge over here, and I can pretty much walk anywhere I want. There's no jumping spot. It's a smooth transition from one value to the next, and I'll get over there as well using this smooth path. The continuous random variable can land anywhere. The discrete only has certain landing spots. And I think it's a decent little way of talking about the difference between these two types of random variables. So you got to ask yourself when you get some data, what kind of values could we see here? Do they jump from one value to the next, or are they smooth? If someone asks you about the number of checkout lines that are open at Home Depot, well, it's either 0 or 1 or 2 or 3 or 4. Hey, that's a discrete random variable. If someone asks you how long it took you to check out, the length in line, well, that's time. Time's continuous. It might have taken you 5 minutes, but it might have taken you 10 minutes. It could have taken you 7.5 minutes. It could have taken you 32 seconds. And so you take a look at the variables you're working with and try to decide, continuous or discrete. And so that's a starting point. Now what we want to do is take a little bit of closer look now at the discrete random variables. We'll come back later and catch up with some continuous. But let's take a look at some discrete random variables. And we start with probability distribution. Okay, when we talk about discrete or continuous random variables, we're talking about the values of x, our random variable. This adds the probability in. This first part of the definition here, table, graph, or formula, that's just talking about the different forms that it's going to be presented. We'll see a little table here in just a second. Before too long, we'll get to the binomial distribution, which will be a formula. I don't think it's going to be a stretch to think about a graph. So different ways of presenting the material. But really, this is the part that matters, that gives the probability of observing each outcome of the random variable. Now, we're talking about discrete, and so the values are this or that other one. It's a jumping nature again. And so we're going to have different values of the random variable. The probability distribution assigns probabilities. Now there's two rules, two probability rules. And if we took a closer look at probability, we would have looked at this. But this should make sense. Probabilities have to be between 0 and 1. Have to be. So if you think about the 5 students with a tattoo, which we're going to come back to in a second, there's a probability of none. There's a probability that none of the 5 have a tattoo. There's a probability that all of the 5 have a tattoo. In fact, there's going to be probabilities attached to the 0, the 1, the 2, the 3, the 4, and the 5. And all those probabilities have to be between 0 and 1. And when I sum them up, the sum of those probabilities has to be 1. Those are the two probability rules that have to be met for discrete probability distributions. Probabilities are between 0 and 1, and they sum to 1. Now, what's this actually look like? All right, so it's going to take a while to build this, and then you guys have the whole slide sitting in front of you if you've printed it out already, which I always recommend you do. But let's take a look at the tattoos. X is a number with a tattoo, and we've already talked about how the values of X, and you can see on this left-hand column you're going to have the values 0, 1, 2, 3, 4, and 5, but I'm going to do them one at a time. Because what I really want to think about in this slide is the probability part. Now, where did that come from? 0.7 to the 5th power. Well, if you think about the 0 students with a tattoo, the first student said, no, I don't have a tattoo. And the second student, ooh, my little mouse skills are going to show here, sorry. But that works. When you think of those outcomes, the 5 ends, where the first student said no, second said no, third said no, fourth and fifth, they all said no. Well, if you go back, and these probabilities that you see on this page are based on the claim that I started with, what's the chance the first student said, no, I don't have a tattoo? And what's the claim that I made at the very beginning? You remember? Look back in your notes. What did I say? The claim was that 30% of all college students had a tattoo. Well, if 30% have a tattoo, what percentage don't? 0.7. And so to get 0, to get the value 0 here, the chance that the first student says no is 0.7. Well, what's the chance the second student says no? and the third, and the fourth, and the fifth, and the sixth. Oops, not the third, fourth, and sixth. The first, 0, the first, the second, the third, the fourth, the fifth. That's where we stop 5. What's the chance? It was 0.7. We multiply those numbers together. So that's what I'm going to do here. Look down the bottom in this little column here. When you get to the 5, what's the chance all 5 have a tattoo? It's not 0.7 to the 5th power. What do you think it would be? That's right. It's 0.3 to the 5th power. And that's where that number comes from. All right, we'll get to that. So that's where this number comes from. And most of the time students see this, they say, okay. Now, what I could do here, and you're thinking, oh, take the shorter route. And I'm not going to in this case. I could just list the values of x in the left-hand column and the corresponding probability. And you see that, and I could just be done with it. But I want to do a little bit more with that. And not necessarily for the probability distribution, because all I need are those 2 columns for the probability distribution. But I want to look at it from this perspective because it's going to help you understand the binomial distribution that we get later. The binomial tends to be tough. Probability distributions tend to be pretty straightforward, pretty easy for students. Binomials, not so much. They tend to be your tougher material. So what I want to do is kind of walk you through this idea, and it'll help you understand what the binomial is doing a little bit later. So if I have one student, if the value of x is 1, this is an outcome that results in one student. In fact, it's the first one in this case with a tattoo, and 4 students without. So the second said nope, third said nope, fourth nope, fifth nope. Unlike the 0, where this is the only way that we can get 0 students with a tattoo, there's no other options out there. All 5 had to say no. When you have a value of x equal 1, when you have one student with a tattoo, well, maybe it's not the first student, maybe it's the second student. So maybe the first one's an N and the second one's a T. Or maybe it's the 5th student that says, yes, I had the tattoo, and the first 4 are N's. And so I can kind of take this T and slide it down, and you can see that there are 5 different ways of getting one student with a tattoo and 4 students without. And actually, when you look at the value of 4 in a little bit lower there, if you flip the N's and the T's, so if you make the first one an N and then you put 4 T's after it, there are 5 different ways of getting one student without a tattoo. Turns out there's 10 ways of getting 2 students with a tattoo. And there's 10 ways of getting 3 students with a tattoo. And if you think about the numbers that I just said, there's one way of getting the 0, there's going to be one way of getting the 5. There's 5 ways of getting the 1, there's 5 ways of getting the 4. And there's 10 ways of getting the 2 and 10 ways of getting the 3. Now, I'm really good with numbers, so I can keep that track. But if you do 1, 1, 5, 5, 10, 10, when you add them up, that's 32. Those are the 32 outcomes that I have the index cards for in my office. And remember how I said you take those 32 outcomes and you kind of put them into the different piles? Only one of them has a value of x equals 0. 5 of them have 1, 10 of them have 2, 10 of them have 3, 5 of them have 4, 1 of them has the 5. And that's what we're doing here. We're thinking about taking those 32 outcomes. Here's 5 of them. And the reason that we do this, and this is where you can see it, the reason that we can do this, what's the probability of this first outcome here? What's the probability the first student says they had a tattoo? Isn't that the 0.3? And what's the probability that the second, third, fourth, and fifth said no? Well, the second saying no is 0.7. The third saying no is 0.7. Fourth and fifth saying no is 0.7. But look at the probability of this outcome here, too. Isn't it the same? And this one? In fact, every time you get one student that has a tattoo and 4 students that don't you end up with this probability? You end up with a 0.3 and you end up multiplying it by 4.7. Now what's this? Well, that's the fact that there are 5, 1, 2, 3, 4, 5 outcomes. And a lot of times what I like to write this, and you see me have written it this way, a lot of times I like to write it this way, 0.3 to the first power. And this is going to be weird for you, probably, but that's okay. And 0.7 to the 5 minus first. It's like, why? Well, you wrote it as 4. That makes more sense. I like this one actually a little bit better. And then I multiply that by 5. And just kind of hold on to that. Okay, just look at that. Don't even worry about it right now. A lot of times I write stuff and people are like, what the heck is he doing? Just hold on to that right now because we'll come back to it in a bit. All right, but this probability, that 0.36015, that's the number that gets slid in right here. And so that's the math behind the probability. Again, this part right here, is not really all that necessary. I'm not going to have you go through this math or these outcomes, but I wanted to show you what it looks like, not for probability distribution works now, but for some things we're going to see a little bit later. Okay, now, the 2. If I looked at the different ways you could get 2 t's and 2 n's, and if you're good at this, and some of you guys will be, rather than going 0.3 to the first power and 0.7 to the fourth power, if I'm talking about 2 students with a tattoo, wouldn't there be 2 0.3s? Wouldn't it be 0.3 to the second power? And then it would be 0.7, and I'm going to write it to this way, 5 minus second to the third power. And some of you guys are keeping track with this, and that's good, and some of you aren't, and that's okay. And then actually, I'll put some parentheses here to make it look more like the other one. You multiply by 10, because there's going to be 10 different outcomes. And that probability is 0.30870, and I'm just going to show you the other ones. This is the 0.3 to the fifth power. This is kind of the opposite of this one here. It's not 0.3 to the first and 0.7 to the fourth. There'd be 4 students with the tattoo, so it'd be 0.3 to the fourth, 0.7 to the first, and there's 5 outcomes, and that's the number you get. The N's, the T's, sometimes students or I start rolling in the back of their heads, and they start like, leave me alone. Here's what you need right now with probability distributions. You need this column right here. You need, look, all the probabilities are between 0 and 1, and if you add them up, guess what it sums to? Yep, sums to 1. This is a probability distribution. That's what we need now. This stuff over here on the right, this stuff, it's good stuff for binomials, but it's not necessary right now. Now this would be considered a table, a probability table. Values of x are listed here. Corresponding probabilities are here. The 2 rules are met. They're all between 0 and 1. And when we talk about the rules, we're only talking about the probabilities here. The probabilities are between 0 and 1, and they sum to 1. All right, now, I don't think it's a stretch for you to see that I could put together a little bar graph where I had the values of x here, 0, 1, 2, 3, 4, 5, and I could draw little bars, 0.16, and here's a value of 0.36, a lot higher, and then there's a 0.3, oops, it would be 0.308, so it would be a little bit lower, and then 0.13, which might be here, and then there'd be 2 low bars here. And we could draw a little bar graph, and if you remember the definitions had a table, graph, or formula. We won't do a whole lot of this, to be honest with you. But that's your first probability distribution, student tattoos. Well, after you get a probability distribution, the next step, the logical question is, well, what do you expect to see? What's the expected value of this independent variable? And I've given you a couple of examples here. I'll put both of them up at one time. The average number of children in U.S. families is 1.86. The average SAT score for college students is 1035. Now, when you think of both of these numbers, and when you think of SAT, I'm thinking about taking out the math and the verbal. I think they've added a section since I saw this last number. But when you look at the numbers, 1.86, can a family have 1.86 children? Does that even make sense? A lot of times I'll ask my students, which of you is the 0.86? And it's kind of a funny, weird way of thinking of things. But a lot of times people will look at statistics and they'll say, you know, this statistic stuff doesn't make sense. You can't have 0.86 children. Doesn't make sense. You can't really have an SAT score of 1035. There's a 0 on the end. You can have 1030, you can have 1040, you can have 1050, you can have 1100, but no one actually scores 1035. That doesn't even make sense. And so what some people will do is kind of throw those numbers away and say, well, that doesn't make sense, so I'm not even going to consider that it makes sense. I'm not even going to allow the fact that it might mean something different than how I want to think about it. I want to think about a family having 1.86 kids and seeing how that doesn't make sense. I'm just going to throw that number away and say that's meaningless. And that's a mistake. And so we want to take a look at the expected value of a discrete random variable. And so we want, what do these averages really mean? What do they mean? And the example that I want to use is the tattoo example. We want to look at, another name for average is the expected value of x. And there's a formula. And I don't ask students to use a whole lot of formulas. This is one that you'll probably use. This is one that's good to know. We're going to multiply the x's. It may look intimidating to some of you. A lot of times I get students that are really not big fans of math, and I always say, well, that's good because we don't do a whole lot of math. There is a whole lot of math going on with what we talk about this semester, but we don't do a lot of it. We let the computer do it for us. But this is one that I'm going to ask you to do. The average mu or the expected value of x, you take the sum of the x's times the probabilities. Now, on that preceding page, we had a probability distribution. We had x's, we had probabilities. We're just going to do some multiplying. Typically, when an expected value is given, there's also a formula given for the variance. And the variance formula doesn't look all that much more challenging, to be honest with you, than the mean or the expected value, but typically it is. And so I'm never going to hold you responsible for the expected, or I'm sorry, I am going to hold you for the expected value, for the variance formula. So when you look and you see problems that say find the mean and the expected value, just do the expected value part. I said that wrong. When I show you problems that say the mean and the expected value, it does the same thing. Typically it says find the mean and the variance. You are not responsible for the variance. You are responsible for the mean. And so you are responsible for this formula. So I want to walk you through it. I want to show you how to do it. It's really kind of easy. One of the things that makes it a little challenging are the probabilities. And you can see these are the probabilities that we had. This is the tattoo example, the same exact number from a couple of slides ago. I've just taken all the binomial stuff out. You get a column of x's, you get a column of probabilities, and really what we want to do is multiply those two columns together. We want an x times the probability of x, and so you see I've added another column on this slide. I got the x's times the probability, and all I'm going to do is take the x times the probability. Now I know a lot of my students are not big fans of math, but you should be pretty good at this. It always cracks me up when students come into my office and we're doing some work together, and they'll sit down and they'll be like, okay, let's see what's going on. I'll explain this is what we have to do, and I'll say you got to multiply these two columns together. And they'll say, okay, I can do that. And I'll say, all right, let's do that. And I'll just go ahead and start writing the value 0 in here, and I'll have some students that pull out the calculator, and it makes me laugh. And I just realize that we're all different. We all have different strengths and weaknesses, and there's a pretty big segment of society that's weak in math or afraid of math, and most of you should know that's the value 0. The same thing here, 1 times the 0.36. I'm ready to write the 0.36015 again, and my students are typing it in inches, and they're like, yeah, you're right. And I was like, yeah, I know. But the rest of this stuff, there's some math involved, right? You got to multiply 2 times 0.30870, and I'm hoping you could do the math in your head, but I'll never ask you to. You'll always have a calculator available, and you can see I just went down and I did the rest. I multiplied all these numbers together, and you can verify if you like, but those are the numbers you get. Well, the thing that this sums to, this number right here, that's the expected value. And in this case, it's the value 1.5. How many of the students do we expect? How many of the 5 students do we expect to have a tattoo? 1.5. And we're back to that weird number, 1.86 children in a family, 1035 for the SAT score. What does that mean? What does that mean? And really how I want you to think of the expected values is they are not outcomes that we expect to see. Expected values should be interpreted as long-run averages, not as outcomes we expect to observe on a single attempt. You should write that down. Expected values should be interpreted as long-run averages. Long-run averages, not as outcomes that we expect to observe on a single attempt. We're never going to, I've sampled students. For years I've been doing this example, and usually multiple times a semester I'll take 5 students from a class. I've never seen 1.5 with a tattoo. Can't happen. Occasionally I'll get a student, I started and I got like this little bit of ink and it hurt and I stopped. It's like, well, you got a really small, lousy tattoo, but you count. You're not half a tattoo. I either get 0 or 1 or 2 or 3 or 4 or 5. Again, I haven't seen 5s. I don't believe I've seen any 4s. I see 0s, 1s, 2s, and occasionally 3s. I've never seen 1.5. The last time I did this, and I had 4 sections, and I saw 0 twice, I saw 1, and I saw 3. That's what I saw in my last semester. 0 twice, 1, and 3. The semester before, maybe I saw 0, 2, 1, and 0. Semester 4, maybe it was 1, 2, 0, and 0. What this 1.5 represents is that if I kept track, and I haven't, but if I kept track of every semester that I've done this, every class that I've done this, every time I've taken a sample, I'm either going to get the value 0, 1, 2, 3, 4, 5. If I kept track of all those semesters over the course of time as I average those numbers together, the 0s, the 1s, the 2s, the 3s, the 4s, the 5s, if I average them together, that average is 1.5. Put another example or another way. Think about the children. The expected number of children in a U.S. families is 1.86. When I look at your family, I look at the family across the street, and I look at a family down the block, and I look at a family from Wisconsin. When I take samples of all these different families and I ask how many children do you have, I'm going to see numbers like 0 and 1 and 2 and 1 and 0 and 5 and 1 and 0 and 2. Then you get the crazy good Catholic family with 12 children and 0 and 1 and 2 and 0 and 1 and 0 and 3 and 2. When you average all those numbers together, you'll get 1.86. It's not what we expect to see in the next family. It's the average of all families, and that's what expected values are. I'll say it one more time. Expected values should be interpreted as long-run averages, not as outcomes that we expect to observe on a single attempt. And so that's what I want you to be able to do. I want you to be able to work with this formula, this expected value formula, and be able to come up with means. Again, the variance formula that usually accompanies it, you're not responsible for, but you are for the means. Now, here's my promise. These numbers have to be between 0 and 1. Occasionally I'll get students, these numbers are too difficult. Can you give us easier numbers? And I'll say, yeah, I can give you easier numbers, and I'll give you numbers that are 0.1 or 0.2 or 0.3. And they're like, no, I want to have integers. And I said, sorry, I can't. The probabilities have to be between 0 and 1. I can't give you whole numbers here. It doesn't work. But I can make them a little simpler than 0.16807, 0.13230. Those are a little bit more challenging probabilities. But I am stuck by the rules of a probability distribution. These probabilities have to be between 0 and 1, and they have to sum to 1. But I can make them maybe a little bit easier for you. So anyway, that's the expected value or the mean of a discrete random variable. That's where I'm going to stop here. Our next step is to talk about the binomial probability distribution, but I'll do that in a different video. So hopefully makes sense. If not, get to work in some of the homework problems, take a look at the textbook, do some reading. You can always email me. You can always ask questions. There's a variety of ways to get in contact with me. Choose one of them and we'll get the material to you. So that's what I got for this video, and I'll talk to you soon. So long.